Thank you. It's a great honor to be here and receive the support from the city of Shanghai. I've just officially accepted in the last couple of weeks the title of founding director of the T.D. Lee Institute. T.D. Lee is a great Chinese physicist and a personal friend and a great inspiration. He was born in Shanghai, and I hope we can do honor to his legacy. So today I'm going to speak about some frontiers of quantum matter. Quantum physics has many frontiers. I would only be able to talk about a very, very small part. I'll try to convey a few ideas to you that could take away with you, but I will not be able to do justice to the whole subject. So, the first beginnings of quantum theory appeared in 1899 when Planck found some discrepancies in the theory of radiation and its equilibrium. But it took 25 years until quantum theory became recognizably in its modern form. That was in 1924 when Heisenberg wrote down the basic equations of quantum theory. So depending on how you count, quantum theory is either a little more or a little less than 100 years old. Yet it remains a very youthful subject. It continues to surprise us. It's still growing. In many ways, it's like a baby. Such has been the progress in recent years and the change in our ideas and the deepening of our understanding in quantum mechanics that some physicists are speaking of a second quantum revolution, which emerges especially from the use of topological ideas in quantum theory, which I'll show you a little bit of. To really understand this, you have to learn the math. There's no way around it. I'm sorry about that. The good news is that if you do learn the math, you'll be richly rewarded. It won't disappoint you. It's very beautiful. The good news for this lecture, I hope, is that you can stretch your mind and get some meaningful impressions about what's going on through simple examples and pictures. So that's what I'll show you today. I'll show you three particular ideas that are bridges between mathematics and physics that lead to important technologies and that are at the frontier of our explorations today. So one is topological flows, the second is topological trapping, and a third is braids. So, topological flows. Well, first, I've mentioned the word topology several times now. I should introduce the basic idea or theme of what topology is all about. Topology is about wholeness and persistence. It studies the properties of bodies or patterns that survive any continuous changes. So that's the idea of persistence, that you can change an object or change a pattern in a wide variety of ways without changing its topology. Topology has to do with the properties that are not changed by continuous small deformations. A nice example of a topological property, the classic example, is the number of holes in a surface. So, for instance, as far as topology is concerned, a donut is the same thing as a coffee cup because you can change from one to the other by continuous motion, as you see here. Or a pretzel with two holes is the same as a mug with two handles, because you can change one continuously into the other. Because these properties, like the number of holes in a surface, are so general and so robust, you can change the body in many ways, they are persistent. And you can get the shape of a body a little bit wrong and still infer its topology. Topology is usually about whole numbers, and whole numbers, if you change them only by a little bit, can't change at all. Now let's look at some more physical examples. Not just the shape of objects, but the shape of physical phenomena. Here we have a vortex and a more complicated object, an anti-vortex. What you see here could be the directions of the flow of wind. And in that case, it would be like a tornado, with the wind going around in a circle. The reason it's topological is that if you trace the direction of the arrows as you go around a circle, so if you follow the pattern, it goes all the way around the circle once. As you follow. Oh. Oh, I have to stay here, I guess. All right. Okay, let me backtrack just a little bit so it still makes sense, I hope. So the vortex could be many things. It's a pattern of arrows, if you like, a pattern of flow. It could be the directions of the wind in a weather pattern, in which case a vortex would be a tornado. And a tornado is something that holds together for a long time. It has persistence. And the reason is that it's topological. The pattern of the wind, if you follow it around the center, you follow these arrows, they go around a circle. They go around by 360 degrees. The angle of the arrows changes, so it winds around a circle once. That's the number 1. It could be 0 as you go all the way around, or it could be 2, but you can't, by small changes, get from 1 to 2 or 1 to 0. It takes a big change, and that's why a tornado, once it forms, is very persistent. It's hard to get rid of because it has topology. An anti-vortex, well, I'll leave it to you to contemplate, but it's very interesting. It goes around a circle in the opposite direction, and is the kind of thing you would get from a vortex if you reflected the arrows in a mirror that's perpendicular to the flow pattern. So I talked about the directions of the wind, but these ideas are very, very powerful in general, these mathematical ideas. So they can be applied to many, many different circumstances, including deep into the world of atoms where quantum theory applies. So these could be, instead of the direction of the flow of winds, it could be the way that the spins of electrons are pointing. Electrons always have a spin that points in some direction, and they could form stable patterns that are like tornadoes. We call them vortices in that context. Or it could be the pattern of magnetic fields. And inside a superconductor, you typically have these kinds of patterns of magnetic fields, or more accurately, magnetic potentials. But in any case, these kinds of patterns can govern the way fields behave and give you stable, non-trivial fields that persist in matter. Here's how topology can lead more concretely to a phenomenon that is really at the center of interest in physics and technology today, and has won several Nobel Prizes, in one form or another, has generated several Nobel Prizes in the last few years. In more complicated forms, I should say. This is a phenomenon of edge flows. If you have charged particles, say electrons, in a strong magnetic field, they tend to circle around in little circular orbits. So if you have a strong magnetic field coming out of this plane, the electrons will tend to move around in circles like that. But if you come to the edge of the material, they can't complete the circle. They can only make half circles. And then if you follow around the half circles that they have to make, you find that there's a current circulating around the edge. That's a current that's implied by the basic topological structure of this flow. So it can't be disrupted very easily. And it's a flow that persists. It's sort of like a supercurrent, a superconductor. It's a current that persists and is very hard to stop and doesn't generate very much resistance. Edge currents are very stable and predictable because they're in the nature of the pattern of flow that can't be disrupted. And those can be very useful properties for technology. Now let me talk about another topological phenomena, that's topological trapping. This leads to essentially new phenomena such as particles inside materials that have a fraction of the electron's charge. You probably have learned in school that the electron is the minimal unit of charge, but in fact, we now know that you can break up electrons or break up their charge and find little particles inside materials that have fractional charge. And surface states, states that are confined to a surface. So let me start with a very simple pattern. So this is a pattern of the directions of spins inside a material if the material is what's called an antiferromagnet. That is, it's a material, a ferromagnet would be a material in which all the spins point in the same direction. So then generating a magnetic field, like the kind of magnet you would buy in a toy store. An antiferromagnet is something that's more hidden. You have to look inside to see the patterns, but people, of course, know how to do that these days. And many materials display this kind of antiferromagnetic spin behavior. But if you heat the thing up or don't prepare it perfectly, sometimes the pattern is a little bit wrong. So one thing that could happen is one of the spin flips, one from being up to being down. You see, I see this guy here is the bad guy. And this flipped the wrong way. So that's one kind of flaw, and it's a very simple kind of flaw that you can generate just by changing one spin without disrupting the pattern on a large scale. But here's a more complicated pair of flaws. You see right here, what's happened is that one of these spins has gone wrong, but then everything else stays the same. So this whole block from here on has the opposite kind of ordering from what it would have had in the flawless antiferromagnet. So this whole long thing here is all wall. Or you might say that there's a domain wall, a wall here between two normal regions of good flawless antiferromagnets. And then here's a second wall. So in this picture we have two domain walls. So there are two flaws which have a topological character. If you move around that flaw, you can move it around, but if you don't change a lot of spins, you can't get rid of it. You can't get rid of it by changing just one spin. You'll always have a flaw left. So just counting the number of spins up and spins down in these configurations is an easy and fun exercise. And in the first one, you find that there are 7 up and 7 down. In the second, you find that there are 6 up and 8 down. And then the third, you also find that there are 6 up and 8 down. So what you discover, if you think about this, what we've shown, is that the topological flaws, these domain walls, act like 1/2 of a spin that's flipped. So in this way, you can get things that behave like fractions of a spin, or in general, fractions of an electron. Sometimes it's even favorable for domain walls to migrate to the surface of a material and stick there, and then you get half particles or half spins on the surface. Those are called surface states. Surface states have very interesting properties often, like fractional spin, which I've shown you in pictures, or fractional charge. Also, since they're stuck to the surface, they sort of want to be on the surface. If you can apply a field and make them move, they will move smoothly along the surface and make persistent currents. So this is another way of getting persistent currents. And physicists are finding more and more materials, not just antiferromagnets, that embody this kind of behavior and embody these kinds of persistent currents that have excellent technological properties. Now let me talk about grades. This leads into the subject of knots, memory, and computation. But at the beginning, it's just grades. You've all seen grades. Some of you have even probably had them on your head. You can make grades, of course, not only out of hair, but also out of rope. And you can find on the internet instructions for making very interesting things out of braids, out of several ropes to make braids. You can make that, for instance. So it's possible to do very, very complicated things with braids. By making simple motions and making many of them, you can make objects that are very complicated and have a lot of structure and are very beautiful too. This is a page from Nature about a remarkable development in physics over the last 10 or 15 years. That is the use of braids to do computing, new kinds of computing, maybe to build what's called a quantum computer. This is a page from Nature that explains it, that is the journal Nature, that explains it pretty clearly, but it's a little complicated to show on one transparency, so I broke it up, and we'll explain it step by step. So inside certain materials that are two-dimensional materials, you can have special kinds of particles that are called anyons, and I will describe what those are, but those are the crucial thing here. So how topological computing works is the title, and the first item is braiding. When two particles that are anyons move either the first one over the second, or the second over the first, these basic moves to make braids, you get effects on the quantum mechanical wave function, which are non-trivial and different. So this is braiding not of strands of hair in 3 dimensions, but of what are called world lines in two space and 1 time dimension. So if you think about a 2-dimensional material, and then the 3rd dimension as time, as you move things around in the 2-dimensional material, the world lines, which trace out their positions in space and time, can make braids. So these are braids of world lines. And the a certain kind of particle, a new kind of particles called anyons, when you have braids of world lines, do very interesting. Braids of world lines where the strands are world lines of anyons make very interesting behavior. So let me say something about these crucial particles, anyons. Ever since the discovery of wave-particle duality in the early days of quantum mechanics, we've understood that the basic units of matter, including light, and electrons, are all the same sort of thing. They can be waves or particles. They can be described either way in different circumstances. And so people in quantum theory talk about wavicles or laves that combine the ideas of particles and waves. And that was a great unification in our understanding of nature. All kinds of particles, all kinds of matter really are fundamentally having the same description. I like to call them not laves or wavicles, but quarticles, which is like quantum particles. So at the level of describing single particles, this is very satisfactory. We have a unified description of all the different kinds of particles. They can be particles or waves, and every kind of matter is described using the same kind of equations. However, when we talk about more than one particle, that is not so good. It has not been so good. When we talk about groups, that is more than one particle, we find that they divide into two great kingdoms, the kingdom of bosons and the kingdom of fermions. Bosons are particles that like to do the same thing. That is, they like to occupy the same quantum state, more technically. So photons are examples of bosons, the particles of light. And a laser beam is an excellent example of bosons in action, because all the photons want to do the same thing. So they're the same color, they move in the same direction, and you can make nice laser beams where the photons are all happy doing the same thing. On the other hand, fermions, the other kind of matter, are individualists. They hate to do the same thing. Technically, they refuse to occupy the same quantum state. This is called the Pauli exclusion principle. So electrons are examples of fermions, and the solidity of matter, the fact that I can't put my hand through this lectern, even though in the atomic description there's lots of empty space the particles could move through, is mostly because of the fact that the electrons are fermions and don't like to be in the same condition, don't like to be in the same state. In a world of 3 dimensions, or more, if you want to think about more, that's all there is. The only consistent possibilities are bosons or fermions. But in a 2-dimensional world, things get much more interesting. It's a case where less is more. The reason is closely connected to the theory of knots and braids. That is, if you go to 4 dimensions, you find that knots become trivial. It's always possible to untie knots if you work in the world of 4 dimensions without cutting. That may be hard to visualize because it's in 4 dimensions, but there's a simple trick that makes it more obvious. If you think about 3 dimensions of space and let the extra dimension be a color, say, where you change the color of your string from black to white, and the amount of blackness to whiteness is a number from 1 to 0, so that's like an extra dimension. Then, if you're trying to untie a knot, and you come to a place where you have to move one strand of another over another, just change the color so they don't match. Then you can move it through. They don't touch each other because they escape the extra dimension, and you can keep untying it freely. And so there are no knots in larger number in 4 dimensions, but there are knots in, of course, 3 dimensions. So likewise, if you talk about world lines, if you have 3 space dimensions and 1 time dimension, that's 4, you can always untie the world lines. But if you have 2 space dimensions and 1 time, that makes, then the grades of world lines are things you can't untie, and they have non-trivial topological properties. That allows you to introduce new kinds of interactions, and nature uses this to make things that are neither bosons nor fermions, but have more general behavior. I named these things anyons, with the idea that anything goes. It's not true that anything goes, but these particles, anyons, can have a wide range of different behaviors. Now, it may seem like science fiction to be talking about 2-dimensional worlds, but in fact, it's anything but science fiction. Most of the worlds of microelectronics, when you have computer chips, they're basically 2-dimensional. And it's very easy to make sheets where the motion of matter is confined to 2 dimensions. So those are essentially 2-dimensional worlds. In some of those materials, in some states of matter, which are now a very active frontier of investigation in physics, the electrons break up. I showed you how spins can break up. That kind of thing can happen in many different ways we're learning. And they can, when they break up, they're kinds of fractions of electrons. So they don't like to do the same thing, but it's not so severe as for electrons with the exclusion principle. You can get intermediate behavior that's in between bosons and fermions. So this is a picture of an electron about to be shattered into several pieces. Doesn't like the idea, but although the electron is disrupted, it turns out the children have new and interesting properties. They have a sort of memory. They're kind of superparticles. They have a very good memory of how they've turned around each other and the topology of the braids that their world lines form as they move around in the 2-dimensional materials. So the enyon is a kind of a superparticle that has memory. And if you have a lot of them, they remember how they've been moved around in the braids, their quantum mechanical wave functions remember, so they have a kind of very powerful memory. This idea that you can encode lots of information and manufacture new kinds of information by moving particles around, if the particles are anyons and make braids, is the basis for topological quantum computing. This may all sound like science fiction, but it's really not science fiction at all. In fact, Microsoft hopes to make money from it, and they're investing billions of dollars in pursuing this topological quantum computing. So this is what it actually looks like when you try to construct these anyons. It's very concrete. It's a 2-dimensional world with semiconductors and superconductors very cunningly arranged to make materials in which the electrons break up, make anyons, and then by applying currents and fields, you can move around the anyons and make them make braids, make their world lines make braids. So that's the basic idea. I hope I've conveyed to you the basic idea of why it's interesting to make braids of world lines and the power of that idea maybe to do quantum computing. And a big advantage of it is because it's topological, because the memory depends on the topology of the braids, you can make all kinds of mistakes without disturbing the topology. So it's a kind of computing that is not subject to errors, and it's not so delicate as other proposals for quantum computing. I say topology is kind. It lets you make small mistakes, because if you make a small mistake, you can't change a number by a lot. And so since topology is about whole numbers, making small mistakes is okay. It's like digital computing in that way. Now, to make useful logical operations is complicated. This gives you some sense of it, but the principle is simple. The future of this subject, I think, is very rich. We can make complicated kinds of anyons that have properties besides just being particles that have no other structure. They could have things like colors, of course not actual color, but extra properties. And then the braids get really, really beautiful and really, really interesting, and maybe even useful. Certainly beautiful. So let me conclude. I hope I've given you a small taste of what's going on at one of the frontiers in this second quantum revolution. Topology can protect delicate behavior by bringing in discreteness. It can lead, in particular, to protected flows, which are persistent and don't dissipate, similar to the way currents in superconductors behave. It can bring in defects with fractional properties, like half a spin or half an electron charge, or half of the fermion statistics to make anyons. And the topology of world lines and the operation of braiding of world lines can support powerful new forms of information processing. So thank you for your attention. I hope I've gotten your interest.